You've got Sir Isaac Newton, one of the greatest minds in history, and you've got your morning cup of coffee. What in the world could they possibly have to do with each other? Well, as it turns out, a whole lot. Let's get into how a 300-year-old law explains something we all experience every single day. So, have you ever noticed this? You pour a fresh, piping hot cup of coffee, and at first it's losing heat like crazy. But then, it just seems to linger at that pleasantly warm temperature for ages. What's the deal with that? Yeah, that little puzzle is what we're going to call the cooling conundrum. And you know what? The answer is actually incredibly elegant. So no, it's not just you. It's definitely not your imagination. Cooling isn't some steady, straight-line process. It really does start out with a bang and then slows way, way down. You can think of it like a sprinter who bursts out of the blocks at full speed, but then eases into a slow jog as they get closer to the finish line. And the person who first put this all together, the genius who first described this whole phenomenon, well, it was none other than Isaac Newton himself. So let's take a look at his surprisingly simple answer. Okay, so here it is. The law itself, Newton's law of cooling, says that the rate an object loses heat is directly proportional to the temperature difference between that object and its surroundings. Now, directly proportional sounds a little bit textbooky, I know. All it really means is this. The bigger the temperature gap, the faster it cools. Simple as that. Here's a really great way to picture it. Imagine that the heat in your coffee is under pressure. So when your coffee is super hot, maybe 90 degrees in a room that's 20 degrees, well, that's a massive 70-degree pressure difference just pushing that heat out. But later, when your coffee has cooled down to just 30 degrees, the pressure difference is tiny, so the heat just sort of trickles out really, really slowly. And if you were to actually plot this on a graph, you'd see this very distinct shape every single time. A super steep drop right at the beginning. And then the line starts to flatten out, getting closer and closer to room temperature, but taking its sweet time. That classic shape is called an exponential decay curve, and it's basically the visual signature of this whole cooling process. All right, so that temperature difference is the main engine driving this whole thing. It's the star of the show. But it's not the only thing going on. There are a few other rules of cooling that come into play. So yeah, besides that big temperature gap, other things definitely matter. Like what's the cup made of? A thick ceramic mug is going to hold heat differently than a thin metal one, right? And surface area is huge. A wide, shallow bowl of soup cools way faster than that same soup in a tall, narrow thermos. And of course, the air around it. A nice breeze is going to whisk away heat much, much faster than perfectly still air. Okay, so understanding this with our coffee is one thing. That's pretty cool. But what's absolutely amazing is how this one simple, elegant law scales up to solve some really fascinating and complex real-world problems. I mean, we see this in the kitchen constantly. It's the reason you have to let a freshly baked pie rest on the counter. It cools down really fast at first, but then that cooling rate just plummets as it gets closer to a temperature that won't, completely scorch the roof of your mouth. But it's not just about pies. Engineers, well, they live and breathe this principle. They use it to design everything from the radiator in your car to these absolutely gigantic cooling systems for power plants. For them, it's all about getting rid of heat as efficiently as possible to prevent a catastrophic failure. And think about your air conditioner or your refrigerator. They are basically masters of Newton's law. They are constantly creating and managing a temperature difference to literally pull the heat out of the air in your room and pump it outside. And now, for the one that might just blow your mind, forensic science. Investigators use this exact same law. By carefully measuring a body's temperature and the temperature of its surroundings, they can actually work backwards along that same exponential decay curve to estimate the time of death. The same physics that explains your coffee cooling down helps solve crimes. How wild is that? So it sounds like a law for everything, right? Well, almost. Like with any model of the physical world, Newton's law isn't perfect. It's incredibly useful, but it's important to know where it works best and what its limitations are. This law is most accurate when you're dealing with smaller temperature gaps. And it works best when the main way heat is escaping is through something called convection. That's just heat being carried away by moving air. But when you get to really extreme temperatures, like a glowing hot piece of metal, another process called radiation takes over. That's heat escaping as infrared waves. The calculations get a bit more complicated then. But here is the fantastic way to see this law in your own life. Think about a bowl of hot soup. In the middle of January, it cools down in just a few minutes, right? That's because the temperature gap between the hot soup and the chilly room is huge. Now, that same exact bowl of soup in the middle of August, it feels like it stays hot forever. It's a perfect everyday demonstration of the law at work. So let's bring it all together. The big idea, the main thing to remember, is that the rate of cooling is all about the temperature difference. This is what gives us that classic exponential decay curve we see everywhere, from our kitchen counters to industrial plants and even forensic labs. And that's Newton's law of cooling. It's just a perfect example of how a simple observation about the everyday world can reveal a fundamental principle of physics. So the next time you're waiting for something to cool, take a moment and just appreciate that invisible curve doing its work. Now that you know the law, what are you going to see cooling differently in the world around you?